In this problem, we're going to find the Thevenin equivalent of the network at terminals A and B. We're going to use a problem-solving strategy entitled Applying Thevenin's Theorem. And if we look at step 2B of that strategy, it says if the circuit contains only dependent sources, okay, and we look, our circuit here only contains dependent sources, an independent voltage or current source is applied at the open terminals, and the corresponding current or voltage at these terminals is measured. The voltage-current ratio of the terminals is the Thevenin equivalent resistance. And since there are no independent sources, then the open circuit voltage is 0. So here's our circuit. And we've got a choice of hooking up a voltage source or a current source. I'm going to select to hook up a voltage source of 1 volt. And you say, well, why a voltage source? Well, if I look, this circuit has 3 nodes. And if I pick this as a reference and have 2 node voltages, and one of them is known, so I'd only have one unknown node voltage here. If I selected a current source, I'd have 3 meshes. This would be known, but I'd have 2 unknown mesh currents. Just simple fact that we have less unknowns. I'm going to calculate the current IA, and the Thevenin resistance is 1 over IA. Now, if we look at this circuit, for instance, let's define that current as I1. And if we look, I1 then is Vx over 1,000. Let's call this current I2. Let's apply Kirchhoff's current law at this node. If we do, we have I2 is equal to I1 plus Vx over 2,000. And if we substitute in for I1, we'll have Vx over 1,000 plus Vx over 2,000. That'll give us 3 Vx over 2,000. Also, let's define this voltage. This node voltage is V2. And if we look at the circuit, V2 is 5,000 times I2. Okay, I2 flows through here. V2 would be 5,000 times I2. So that's 5,000 times 3 Vx over 2,000. That'll give us 7.5 Vx. Now let's do KVL around a loop. Let's do it around this loop. Starting here, we'll go around clockwise, so we'll have minus Vx plus 1 minus V2 equal to 0, or Vx plus V2 equals 1. Now if we substitute this in for V2, okay, we'll have Vx plus 7.5 Vx equal to 1, 8.5 Vx equal to 1. So then Vx is 1 over 8.5, and that's 0.1176 volts. So now we're have solved for Vx. We can now calculate the other node voltage V2. Now to calculate IA, we need to apply Kirchhoff's current law here. We know this current is 1 over 2K. So by applying Kirchhoff's current law, we get IA is equal to 1 over 2K plus I1. So there's the application of Kirchhoff's current law. And we know that I1 is Vx over 1,000. So then we have 1 over 2K. We know that Vx is 0.1176 over 1,000. And this is 0.6176 milliamps. So then R Thevenin is 1 over IA, which is 1 over 0.6176 milliamps, which is 1619 ohms. So our Thevenin equivalent is just a resistance with a value of 1,619 ohms.